Hi, so today's lecture we are going to go through and actually derive the kinematic equations for constant acceleration. These are going to be the equations that we're going to use to analyze kinematic motion for the first whole section of the course. Before we get into that, though, I want to recap where we are right now, how we've got to this point in the course. So we started with just how we describe motion and using those words position, velocity, and acceleration and what they mean. Now, these three words all have magnitude and direction. They're what we call vectors. In some upcoming lectures and later on, we'll get into some more formal mathematical detail of how we treat vectors. For now, if you recall, the one-dimensional sort of motion we've been looking at so far, this direction was essentially the sign. So we could have positive or negative velocities. If we called, say, right, the positive direction in our coordinate system, if we had a velocity to the right, it was positive. If we had a velocity to the left, it was negative. Likewise for acceleration or position. We then moved on to how to visualize motion, starting with motion diagrams. This was sort of like the one pictured here, where we had some coordinate system we've defined, and we had just an image, in this case a dot because we use the particle model, of the object at different instances in time, all equally spaced in time. And you can add velocity vectors. We could have also had acceleration vectors if we wanted. But that sort of gave us a nice visual aid sort of description of what we expect or know the motion to be. We then, in the last class, sort of looked at graphical representation. So we could graph position versus time, and we see some non-uniform motion like this, where we have a curved position versus time graph. We could also plot velocity versus time. In this case, for the corresponding motion, it's a straight line. On the position versus time graph, the slope of that graph is the velocity, and you can see in here the slope's getting steeper and steeper and steeper and steeper, which means the velocity is getting larger and larger and larger in the positive direction. And then if we had the acceleration, it would have been just the slope of that velocity versus time graph. So we looked at those graphical representations. And then in our quantitative analysis, we had velocity was defined as the change in position over the change in time, where that's the average velocity for whatever that time interval is. We then took the limit of small delta t to that delta t going to zero, and then that ends up being just the derivative, and it gives us our instantaneous velocity, the velocity at that instant in time where that derivative is. Similarly, the acceleration was defined as the change in velocity over a given change in time, and that was the average acceleration over that time interval. Again, taking the limit of that delta t going to zero, we get the derivative of velocity with respect to time, giving us the instantaneous acceleration. Going the other way, if we know some change in, or we want to know some change in position, and we have the velocity as a function of time, we can just integrate the velocity function with respect to time over that time interval. What this means graphically, again, we already discussed how the derivatives on a plot are slopes. So if we have a position x versus time t, and we take the derivative dx dt, we get the slope, which gives us the velocity. We can go the other way, though. If we have the velocity as a function of time and we take the integral over two time intervals, the area under that curve gives us that change in velocity, change in position between those 2 points. So this is where we've got to. Hopefully we're getting comfortable with it as we go. What we're going to do now is use these sort of things and derive our kinematic equations. So how can we derive our kinematic equations for constant acceleration? The first way we're going to do this is just do some calculus on a constant acceleration. So if we take our acceleration and we say that that's equal to some constant, and we're going to call that constant a naught, some value, right? I can then just do some calculus on that. I know that since acceleration is the derivative of velocity with respect to time, that allows me to integrate that acceleration with respect to time from t equals 0 to some time. And that's equal to the integral of my velocity of dv from some initial velocity to some final velocity. And then if I do those integrals, well, that's just going to give me a naught t minus a naught 0, because that lower limit's just 0. And that's going to be equal to, well, integrate 1 and you get the constant, so just impose that limit, those limits, and we get v minus v naught. So just integrating that constant acceleration gives us our velocity at some time t is equal to our initial velocity plus our acceleration, our constant acceleration times time. This is actually our first kinematic equation. I'll just write first kin equation for constant acceleration. If we want the velocity at some later time t, it's just our initial velocity plus how much that velocity has changed, which is our acceleration times time. We can do the same sort of thing now that we know our velocity is a function of time. We know that velocity is equal to the derivative of position with respect to time, so that allows us to do that integral again. We can integrate the velocity with respect to time from t equals 0 to some later time t, and that's equal to the integral of dx from some initial velocity x naught to some position at some time t. Now, because I have this function of velocity, I can actually substitute that inside the integral, and I am integrating now v naught plus a naught t with respect to time from t equals 0 to some time t. And that's going to be equal to, well, again, integrating 1 with respect to x gives me x, and evaluated at those limits, x minus the initial position x naught. So now, how do I do this integral? Well, the first term in it, the v naught, gives me just v naught t. The second term gives me 1/2 a naught t squared. And this is equal to x minus x naught. Forgot the subscript there. So this, rearranged to find my position at some given time t, is equal to the initial position plus the initial velocity times time plus 1/2 a naught t squared, right? And this is actually my second kinematic equation for constant accelerations. And it, so the position at some time t is equal to the position I started at, plus how far I've moved based on my initial velocity, plus how far I would have moved due just to the fact that my velocity is changing over that time. So we have two kinematic equations, this one here and this one here, that we got essentially just from integrating our constant acceleration. We integrate it once, we get velocity. Integrate it again, we get position. Turns out there's a third one, right? So the third kinematic equation that we're going to use is really just a combination of those two. So I'll leave this one here and write the first kinematic equation was velocity was equal to the initial velocity plus the acceleration times time. This is my other one. I can rearrange this and solve for time, which gives me time is equal to velocity minus initial velocity over acceleration. I can then take this time and substitute it into that equation, so I no longer have the time variable in there. And what happens when we do that is this, that position at some later time t is x naught plus v naught times, instead of t, we make that substitution over acceleration, plus 1/2 a naught v minus v naught over a squared. I'm going to just do some standard algebra on this. Oops, didn't want to do that. V minus v naught squared all over a, plus one of these a's that are squared are going to cancel. So this ends up being v squared plus v naught squared plus, minus 2v v naught, that cross term, all divided by 2a naught. We can multiply this to get the common denominator, and that'll give us 2v naught v minus 2v naught squared plus v squared plus v naught squared minus 2v naught. All of that divided by 2a naught. And things start to simplify. Those two terms cancel. This one cancels with the 2. So we're left with my position at some later time t is equal to x naught plus v squared minus v naught squared all over 2a. Now I can rearrange this and I end up with x minus x naught times 2a is equal to v squared, and I'm going to actually bring the v naught to the other side as well, v naught squared plus 2a. This is our third kinematic equation, where we can now get the velocity, it's squared, so we have to be careful what sign we have if we actually solve for the velocity, but we have the final velocity, or some velocity at a later time t squared, is equal to the initial velocity squared plus twice the acceleration times the displacement, or the change in position over that given time. And this is our third kinematic equation. So that's one way to derive these three equations. We have, start with constant acceleration, integrate it, we get our velocity as a function of time, integrate that, we get our position as a function of time. Then we can take those two equations and sort of remove the variable t from it, and we get our third kinematic equation. Now, this all makes sense also graphically as well, all right? So if I were to just do this in terms of plotting, right? If I were to plot my acceleration as a function of time, if it was constant, it'd just be a flat line, right? And if I wanted to go from some t naught to some final t, the integral of that is the area under the curve, right? So that integral is that area, and we know that the change in velocity is equal to the integral, or the area under the curve. And what's the area of this rectangle? Well, the height is that constant acceleration a naught, and the base of that triangle is delta t. So I know that the change in velocity is equal to a naught delta t, or if I want to write this in terms of v minus my initial velocity, the change in velocity is equal to a delta t, I can get the exact same equation that we just derived, a naught delta t. The only difference is the way I'm writing this. In the above calculus derivations, I was calling the initial time 0, so this delta t would just be the final t, but it's the exact same thing. Likewise, we could get the second kinematic equation as well, just totally consistently. If we had that velocity as a function of time, this velocity is linear, y equals mx plus b, so y is equal to slope times variable plus the intercept here. So I have some intercept, some straight line, that's the slope is my acceleration. And if I wanted to go between t naught and some later time t as well, again, I know that my change in position is equal to that area under the curve, right? So what is the area of this underneath that curve? Well, if I wanted to just do this geometrically, I could cut this into two different shapes, right? This underlying rectangle here, and then I'll switch colors and do this triangle up here, right? And hopefully we remember how to calculate areas. The rectangle we've just done. What's the height of this rectangle? Well, that was my initial velocity. So that area is equal to the height, the initial velocity, times, again, the delta t. And now I just have to add the area of this triangle. The area of that triangle is going to be half the base, and the base is delta t, times the height. And what's the height of this triangle? Well, it's going to be v final, or v at t, some final t, minus v naught. This is my delta v, right? We can do a bit of substitution here, since we know, we'll go all the way back here, what that delta v is. That area under the curve is v naught delta t plus 1/2 delta t times a naught delta t. Or if I want to simplify all of this, I get the second kinematic equation. Delta x is equal to v naught delta t plus 1/2 a naught delta t squared. To write this in the familiar form from above, this is x minus x naught is what delta t means. V naught delta t plus 1/2 a naught delta t squared. Again, the only thing that's really different here is I've been writing delta t to give this delta t down here, whereas in the previous calculus I just set t0 equal to 0, and then all of these delta t's just become t's. But the point is, calculus relates to plotting and graphs, and you can sort of just draw, starting with a plot of a constant acceleration as a function of time, and calculating areas under the curve. You get the same answers, which makes sense. That's what calculus and those integrals do. So those, just to summarize, we have our three kinematic equations of constant acceleration. We're going to use those. Those describe motion of any object that has a constant acceleration, which turns out is quite a common thing. So that's it for today. In our synchronous meetings and in the future, we're going to work through examples, and we're going to use these three equations all the time, and you'll see them frequently on the homework and throughout the course.